recursive algorithms. Yeah. The topic, yeah, I think most of you have some experience about recursive algorithms. But here, for this module, we will learn in some systematic way. Yeah. So because it is very important. Yeah. So we need to really understand recursive algorithms. Part A, Introduction to Recursive Algorithms. Yeah. 8.1, First View of Recursive Algorithms. All right, yeah. So first, let's consider that recursive thinking. Yeah, the thinking way is quite different. Yeah. Recursive, non-recursive, let us compare these two different thinking ways. Yeah. We are used to non-recursive thinking. Yeah. But here, to solve a large class of computing problems, recursive thinking is a very useful method. Yeah. All right, so let's see the question, why recursive thinking is important in problem solving. All right, yeah, so we're used to straightforward, non-recursive thinking in problem solving. Yeah, because we feel comfortable, right? Yeah, so we can see, what we are doing step by step in a non-recursive way. Yeah, but for the recursive thinking, you need to make some assumption. Yeah, you need to assume that some special case, some you make your problems, yeah. So make your problem smaller, make your problem in smaller problem size. Yeah, here. So here we are targeting the problem size. Yeah. And we know the smaller the size in general. Yeah, so here in general, the smaller the size, the easier the problem. Yeah, so we have this basic fact. Yeah. So with that, yeah, that means when we solve problem, we should start from small problem sizes. Yeah. So that's easy to understand. Yeah. All right. So then change, make, yeah, let's say make the size larger. All right. Yeah. So that's the quite natural way. Yeah. All right. But, so here, but the question, we cannot go through all problem sizes, right? Nobody can go through all problem sizes, all right? Yeah. All right. So from implementation point of view, nobody can go through all the problem sizes. Yeah. But our thinking should cover all problem sizes. Think about this logic. Implementation point of view, nobody can go through all problem sizes, but our thinking should cover all problem sizes. All right? Yeah. So here you can see there is a gap. There is a, significant gap between these two things. Implementation point of view, thinking point of view. A big gap. Yeah. How to bridge the gap? Recursion. Recursion helps us bridge the gap. Recursion. Right? Recursive thinking, recursion. Because for recursion, we can make reasonable assumption. Okay? Although we cannot go through all problem sizes, but we can make a reasonable assumption to cover some of the problem sizes. Then by recursion, we can cover all the problem sizes. That's the idea. Okay, assumption. Yeah. So here, yeah. For conclusion, assumption plus assumption is reasonable, but it does not come from nowhere. All right, it comes from certain states of the problem. Yeah, we have those states. That's what we say, initial states. Okay, initial states. Yeah, we have that. Okay, yeah. So assumption plus recursion. Okay, yeah. Then for all sizes. Yeah. So in this way, we bridge the gap. We can cover all the problem sizes. Yeah. So that is the basic idea of recursive thinking. Yeah. So with that, some problems can be solved in both ways, non-recursively and recursively. Yeah. Because sometimes people prefer using the non-recursive way. Sometimes people prefer recursive way for the same computing problem. Now, we will have that kind of situation. Now, each way, there is some advantage and disadvantage. Okay? Yeah. All right. And we will discuss, the relative important points. Yeah. All right. Now, the one of the most important advantage for the recursion, power of recursion. So this is big advantage. Yeah, the power. Yeah, we like the power. It's very powerful. Yeah, so this point is big advantage for the recursion. Okay. All right. Some relatively hard problems can only, parenthesis only. Yeah, yeah, because, you know, in our textbook, it said it does not have this, all right? Be solved by recursion, because the author of our textbook, the author feels any computing problem, if it can be solved recursively, then there must be a non-recursive version for it. Yeah, but in the real world, we will have many times we couldn't find non-recursive solution. Yeah. In today's class, we will have a question, simple question. And it is extremely hard to find a non-recursive solution. Okay, yeah. So for that reason, I put this parenthesis only. Yeah. Okay. All right. Yeah. So then we may compare non-recursive way, we call it iterative way. Yeah. Sometimes we prefer this way. Yeah. Iterative way. Yeah. Because there is some advantage. This advantage, we like to have it. If it's possible, we like to have it. Yeah. So what's that? Yeah. It is less resource. Less resource. We like this part. If the implementation is not too hard, then we like to use the iterative way, so we can use less resource. Right? Yeah. Why? Yeah. Later I will have chance to explain that. Yeah. Recursive way, yeah, it is powerful. Yeah, this one. That's the, you know, most important reason we like to take this recursive solution. So powerful. Yeah. But the power is not free. You have to pay the cost. The power has some cost, relatively high cost to pay. So what is the cost? This is the cost. Consume more resource. Yeah. And we need to pay for that relatively high cost. Yeah. But implementation is easier. Yeah. Implementation for the recursion. Yeah, that's the advantage part, easier implementation. We like this advantage. Yeah. Here you can see two advantages. One, powerful, another, easier implementation. Yeah. All right. But the cost, yeah, you may ask why the cost is high, right? Yeah. Why the cost is so high? Yeah. You need to go to the internal implementation for the recursion. Yeah. Inside computer, you know, high-level programming languages, we know the recent high-level programming languages all support recursion. They need to manage the resource for the recursion in a special way. Yeah. Here, let me explain a little bit. Yeah. Inside the main memory, so suppose this box is, you know, in computer main memory. Yeah. The resource mainly there, main memory hard drive, right? Yeah, we treat as computing resources. Yeah. Here in main memory, how to implement recursion. Recursion. Implementation. All right, yeah. So we need to use a special data structure called a stack. Okay, yeah. in CS3250, you learn the data structure, stack structure, first in, last out, right? So it's processing order, first in, last out. Yeah. All right. So when you, because in recursion, you need to push your steps, in the stack one by one. Think about that, one by one. Yeah, push into the stack. Yeah. The first thing you push in, it's at the bottom of the stack. Right? So that's the recursion levels. Yeah. Think about recursion levels. Yeah. So you call the recursive function, but the value is not available, then you push it into the stack. And this unknown value relies on another recursive function call, but that value is still not available. So you can only push into the stack another time, and so on. Yeah. In this way, you can see the stack, could be very deep. The stack could be very deep. Okay. And a deep stack consumes a lot of resource. Think about that. Deep stack consumes a lot of resource. If your algorithm uses too much memory resource, it could be very slow. Okay? It could be very slow. Yeah. And there is a possibility. Remember, some of you may have the experience to have the runtime errors called stack overflow. Yeah, think about that. Yeah. The stack, you run out of the memory resource. The memory resource available cannot handle that deep stack you need for your algorithm. That could happen. In that situation, you will have a stack overflow problem. Okay, so your program terminates due to that reason. Run out of resource, that reason. So that's the problem we don't like to have, right? Yeah. So that's the disadvantage part. When you use the recursion, that could be the disadvantage part. Yeah. Even with that disadvantage, yeah, because its power is so big, its advantage is so big, and we like to have this recursion tool in our toolbox. Okay, it's a powerful tool in our problem-solving toolbox. All right, yeah. So that's the, basic discussion for recursion. Yeah. Next, I like to use this recursive thinking to solve a very simple problem. In this simple one, we can have our first view of recursion understanding. Yeah. Yeah, we will try to see from a new angle in our understanding. Yeah. The problem is very easy. Given a non-negative integer n, yeah, find its factorial, n factorial, this notation. Yeah, so we are familiar with this notation, right? Yeah, and so it's a simple problem from the textbook. Yeah. Very simple. And usually we do not rely on recursion, right? Solving a simple problem like this, why we need to use recursion, right? We don't need. Yeah. But here, as an example to get a good understanding, yeah, we need it. Yeah. We like to view it from the recursion point of view. Yeah. Method one, yeah, iterative way. We just write a for loop. We can implement, find its value easily. And let's start from the definition of recursion. We know this is the definition. The product of these n consecutive positive integers from 1 through n. Yeah. And here, remember, in our given question, we say non-negative integer n. That means n, it is allowed n to be 0. Yeah. This case is included. Yeah. But in fact, what is the 0 factorial? Yeah. If you look at from this definition part, it's not easy to guess what is the value for the 0 factorial. Some people, if they use their intuition, they may guess 0 factorial should be 0, right? Yes, by intuition, because 0 do multiplication. How do you? We know 0 multiply anything must be 0. Yeah. Then there is a natural way to guess the value by the intuition, 0. But here our assumption, this is assumption. The assumption tells us it's not 0. It's 1. But how to understand? How can you see it? How do you see it? 0 factorial equals 1. Yeah. Although you say people make assumption, but assumption, when you make assumption, you cannot cause any contradiction, right? If you make assumption, but later your assumption contradicts your logical results you derived later, then your assumption is wrong. You cannot make a wrong assumption, right? So you need to make sure this assumption is correct. This one is correct. No contradiction. Yeah, we will see that. Later we will see this assumption is correct. Yeah, no contradiction. Okay, yeah. So that's the reason we can make this 0 factorial equals 1 assumption. Okay, compatible with all our logical reasoning. Okay, yeah. All right. Here, based on a definition, people can easily, yeah. So we will answer this question later. Okay, yeah. Here, still, we need some more information. We do not have sufficient information at this point. Yeah, we need to collect a little more information. All right. Implementation is straightforward. A for loop, a simple for loop. Yeah. So here I do not need to write it out explicitly. Yeah. But method 2, yeah, recursive. This time, let us consider the recursive way. All right. So the general idea, so when we do the recursion, the general idea is like this. Yeah. General problem approach. Yeah. Divide and conquer. Yeah. It's a commonly used method in problem solving, divide and conquer. Yeah. So this one is a big topic, divide and conquer. You know, this in problem solving, this is a big topic. Yeah. And in our module 2, not module 2, module 4, we will cover divide and conquer. The whole module. Yeah, we will study divide and conquer approach. Okay, yeah. But here we already use it. Now, when we do our recursion, we need to take this divide and conquer approach. Yeah. All right. First, the problem is easier when the size is smaller. So when we start solving a given computing problem, we start from the cases with very small sizes, because that's very easy. Yeah. Yeah. All right. So after that, when you work on a problem of the current size, yep, because eventually you need to work on any given size, right? Problem, any given size. Yeah. So we treat it as current problem size. Assume that a problem of a smaller size has been solved. So here, this is assumption. Yeah. That's what I talked about in the previous slide. That assumption, we can assume that. Yeah. Why we can assume that? It's not baseless. We cannot make baseless assumption, right? Yeah. That assumption has a solid base. This is its base. Okay, so that's why we call it base cases. These smaller problem sizes, we call it base cases. Yeah. Could be multiple cases. Sometimes one base case is enough. Sometimes we need more than one base cases. Yeah, base cases. So that's the reason we can make assumption like this. Okay, all right. Then, but there is a gap. The current problem size and the previous problem size smaller, current problem size larger, and how to fix the gap between these two, the same problem with two different problem sizes. There is some gap. We need to fix it. Okay, yeah. That fixing formula, the formula to fix it, that is the recurrence relation. If we can discover a recurrence formula or equation, then we can fix the gap between two different problem sizes. That's the basic idea for the recursive method algorithm. Yeah. All right. So based on this general description, so this is general for all recursion type solutions. Yeah, all. Yeah. And the problem size larger, smaller, that corresponds to divide and conquer. Yeah. You divide. When you divide the given problem, you make it smaller, right? You make the problem sizes smaller. Then you conquer. Conquer, here we use recursion to conquer. That's legal, yeah, because the recursion is supported by high-level programming language. So it can be implemented. So it's legal. Yeah. So we conquer that. All right. Then you need to do the step number 3. You need to fix the gap. Okay. So then you complete that divide and conquer, the whole method here. Okay. Yeah. That's the divide and conquer understanding of recursion. Okay. Yep. Now let's work on this factorial problem. Work, especially mainly that recursion part. Yeah. All right. So when we start from the definition. This is the formal definition of the factorial. Yeah. The left-hand side n factorial. Yeah. Let's assume we do not know the answer. Okay. Yeah. That n factorial, that big number We do not know its answer. Yeah. So our goal, we want to find its answer. Okay. In that way, we introduce a representation for it, a function called f of n, capital F function with problem size n. Okay. So the left-hand side, we use f of n to represent n factorial, its value. Yeah. All right. With this representation, now we try to look at the right-hand side expression. Right-hand side, this product of n consecutive non-negative, yeah, actually positive. Yeah. Here there is no reason, no zero value involved. So we can call n positive integers. Yeah. All right. Then we apply divide and conquer. Yes. Here we need to use that divide and conquer view. How to divide? The divide way is a special way. We just chop down the last operand number. Yeah. Your product. You have n operands in your product, right? There are n operands in the current n factorial product. But now we chop off the last operand. Why we chop off the last operand? We want to reduce the problem size. The reason, so here, I mentioned this idea before. So the idea, so let me recall, we used, that's the problem size reduction. Problem size reduction way. Here, we reduce the problem size. But how do you reduce? The question, how do you reduce the problem size, right? Yeah. Here we use a special way to reduce the size by 1. Only the size is 1 smaller than the current problem size. Okay, so we chop off only 1 operand from the product. Okay, yeah, 1 size reduction. So it is one of the special cases. One of the cases, yeah, when we do divide and conquer. Yeah. Later we will have many different cases. Yeah. Here is the simplest case. 1 size reduction case. Okay, yeah. All right. After that reduction, yeah, how to represent this part? Yeah. We have the definition, n factorial, capital F of n. Can we use this notation, this function, to represent the product at the left-hand side of the vertical bar we use to chop down the last operand? Yeah. That is capital F of n minus 1. Yeah. Capital F of n minus 1. Okay? Yeah. So its expressions simple. Yeah. Next, then the original formula can be represented in the simple way. Capital F of n equals F of n minus 1 times n. That's the recurrence relation. This recurrence relation is used to fix the gap. Fix the gap between 2 problem sizes, right? One problem size, size n. Another problem size, size n minus 1. And their relationship, this whole equation is the relationship. Okay? Yeah. So with this recurrence relation, we can implement it easily. right? Yeah. So, but here in our representation, we require that n greater than 0. Yeah. Otherwise, we may have trouble, right? In this representation, we may have trouble. So n must be greater than 0. Okay, all right. Yeah. The question, how to see that 0 factorial equals 1? Now we need to answer this question. Yeah. Because without any reasonable explanation, you cannot make assumption like this. Because you may have some contradiction if you make arbitrary assumption. Yeah. You have to find some good reason to support your assumption. Here, we can do it. Here, let us write our recurrence relation in this equivalent formula. Yeah. F of n minus 1 equals f of n over n. That's equivalent from our recurrence relation, right? Yeah. And from this formula, yeah, if we plug in n equals 1, can we make n equals 1? We plug in, so we have left-hand side, f of 1 minus 1, that's 0. F of 0 equals the right-hand side, f of n over 1. F of 1, yeah, f of 1, we know 1 factorial, right? 1 factorial equals 1. 1 over 1 equals 1. So that means f of 0, that is a 0 factorial, right? Yeah, because based on our, definition, if we do extension, we may need to do extension a little bit. That corresponds to 0 factorial, okay? F of 0 corresponds to 0 factorial. So this tells us, yeah, this equivalent formula, equivalent to the original recurrence relation, that results in this 0 factorial equals 1. Yeah. That's the reason if we make assumption like this, no contradiction. It's compatible with our recurrence relation. Yeah. So that's the reason we can make this assumption. Okay. All right. Yeah. So here, the conclusion, the final conclusion. It is an interesting way to solve the problem. Yeah. Why I say this way? Because to calculate n factorial, we don't need a recursion, right? Yeah. Nobody needs recursion to calculate n factorial. But for this simple example, we see it's a different way from the iterative method implementation. Yeah. But it's an interesting way. Interesting because the idea, problem size reduction, and this idea probably can help us to solve many relatively hard problems. That's the value we like to have. Yeah. For future, yeah. So let's say the purpose, main purpose, yeah, for solving future, relatively hard, yeah, because how to understand hard problems, right? For different people, the understanding could be different. Yeah, let's say relatively hard problem. That's the main value of this method. Okay, that's the importance of this method. Yeah. All right. So here you see some introduction. So here I use this example as introduction for the recursion. Okay, recursive method, and then later we will try to expand to cover several different cases, commonly used cases in recursion. Yeah. All right. Yeah. 8.2. Here, I like to use another relatively simple, but actually it's not that simple, yeah, but relatively simple problem, computing problem to show the power of recursive algorithms. Yeah. How can we show the power of recursive algorithms? Because later, after we solve the problem by recursion, you will see without using recursion, it is almost impossible. Yeah, I cannot. Yeah, I myself, I cannot solve it without recursion. Yeah, but I don't know if some other smart problem solver can do it. Yeah, it's that could happen. Yeah, yeah, but that would be extremely hard to find an iterative solution. Okay. All right, so let's look at the problem first. Yeah. Our computing problem number 7, Tower of Hanoi. I think you did this before, yeah, because still in CS3250, yeah, we solved this one. Yeah, because I used the material from my notes when I taught CS3250. Yeah, it is in our textbook, the Tower of Hanoi. You can find, the problem in our textbook. Yeah, but the solution. So I need to use some material from my CS3250 notes. Yeah, here. All right. Yeah. For example, the diagrams. So I took the diagrams from that class. Yeah. And to show the idea, so here we just use 3 disks. Yeah. But our goal, we need to solve for n disks. Yeah. Any positive number n disks. So much harder. 3 disks already not trivial, right? Yeah. I think you know the solution, but for kids, it may not be easy, right? For young kids, okay? Yeah. This one is a puzzle. Yeah. So for many young kids, they like to, work on this challenging puzzle. Yeah. It's a puzzle. Yeah. First, let's understand the rules, the basic rules. All right. Number 1, only 1 disk can be moved at a time. Yeah. You cannot move 2 disks, okay? 1 by 1. Yeah. So every time move 1 disk from 1 peg to another peg. Total, you only have 3 pegs. Yeah. Peg 1, 2, 3. Yeah. All right. So you can only move from 1 peg to another peg. All right. But it will be covered in another rule. The second rule, a disk cannot be placed on top of smaller disk. Yeah. When you move, you cannot place a larger disk on top of a smaller disk. That rule. You have to follow certain order. Okay? Because this rule will make the puzzle harder, a little harder. Otherwise, without this rule, the puzzle is very easy. Okay? You can move in arbitrary way without this rule. Yeah. So this rule is important. Yeah. Make it harder. You have to maintain certain rule when you move your disks. Okay. Number 2. Number 3, all disks must be stored on a peg except while being moved. Yeah. This number 3, that's what I mentioned at the early time, because you cannot place 1 disk on the table. Think about, you place one disk, you put it on the table, then it's much easier, right? Because you have a lot of spaces on the table, right? You know, you can, when you have many disks, before you put it on the destination peg, you use the large space area on the table or on the ground even, okay? On the ground, you know, that's the violation, because that would make the puzzle too easy and trivial, okay? Not challenging, okay? Yeah, for that reason, we need to eliminate. We do not allow this happen. That's our rule number 3. Yeah. Then to solve it, it's non-trivial. Okay. And yeah, so here for the 3-disc puzzle, you know, for young kids, it's non-trivial. Yeah. For us, it's very simple. But our goal, we need to solve the n-disc problem. That's non-trivial. Okay. Our goal is for n-disc, but here, because it's hard to draw the general n-disc case here, right? Yeah. So here, the 3-disc case, just for some simple illustration here. Okay. Yeah. Later, we need to treat it as n-disc case. Yeah. All right. Yeah. Yeah. So the reference from our textbook. Yeah. Section 2.4. Yeah. Here. Yeah. All right. So the analysis. The question: how to solve the general problem with n disks? Yeah. If you want to solve it directly, then it's hard. Yeah. I think you can imagine n equals 10 case. Yeah. We do not require, you know, n equals 100, 1,000, that kind of relatively big numbers. Let's just imagine n equals 10. How many people in the world can solve this puzzle with 10 disks? Right? Yeah. I cannot, you know. Yeah. Because I may need to spend the whole day to solve it. Okay. I may need to spend the whole day if I work on a 10-disc puzzle, Tower of Hanoi. You know, I do not have that patience. Okay, the whole day doing things like this. Yeah. All right. Yeah. So here, the point I like to convey here, it's non-trivial. That's my point. Yeah, it's non-trivial, you know. Yeah. All right. Yeah, non-trivial. Yeah. So we have to find some smart solution for it. Otherwise, we cannot solve it. Yeah. That's the point I like to convey here. All right. Yeah. We just learned recursive thinking. So here we will use that. We will use the power of recursive thinking here to solve this non-trivial computing problem. That's the point. Okay. All right. So let's start. Yeah. We start with here, the strategy. When we start from simple cases. Yeah. Here, when n equals 1, n equals 2, trivial, right? Yeah. We can call these two cases trivial. Yeah. So I do not even need to show you how to solve, right? Yeah. Everyone can see it clearly. Okay. So I do not need to show you how to solve these two simple cases. Okay. All right. Yeah. So here, after that, so here we can comfortably assume we have these two solutions for n equals 1, n equals 2. We already have the solutions. Okay. Yeah. So we can move to the next step. The thinking here. When we solve the problem of size 3, yeah, after 1 and 2, we need to move to 3, right? Yeah. So we increase the problem size, grow it larger and larger. Yeah. But when we work on problem of size 3, we can assume that we have already solved the problem of size 2. Okay. Nothing wrong here, right? Yeah. Yes, we have that solution. Why we cannot assume that, right? We have that solution in our pocket. Why we cannot assume that, right? If some people challenge us, we just take it out from our pocket, you know. Here is the solution, all right? Yeah, so that's why we can make the assumption like this, okay? All right, then by recursion, yeah, there is a gap, right? There is a gap between solution of size 2 and the solution of size 3. Yeah. The recursion, we need to fix it by, you know, some special recursion. Okay, all right. Yeah, so here for n equals 3, we need to do some work to fill the gap. All right, yeah. So it's non-trivial, yeah. And we need to do some work here. Yeah. So the work we need to do, yeah, we need to get some experience. Yeah. Otherwise, if we do not have any experience, we do not feel comfortable for the discussion. Yeah. So in our next slide, let's do some experiment. Moving 3 disks. Yeah. We will do some concrete step-by-step work to solve the 3-disk puzzle. All right, yeah. So when we start, this is the original state, okay? 3 pegs, 3-disk power, you know, yeah, in natural order. Yeah, we can call it, the order is natural. Smaller disks on top of larger disks, this order, okay? Yeah. All right, the first step, we move the top disk to peg 3. This peg 1 to peg 3, that's legal, right? Yeah. So we follow all 3 rules. So this move is legal, okay? So we can go to the next step. Then the middle disk, we can place it on peg number 2. That's also legal, right? Yeah, no violation on any of the 3 rules. Yeah. After that, moving disk 1 back to peg 2. Yeah, this time also legal, right? Yeah. Yeah. All right. Step number 4, then the bottom disk, this time, the bottom disk, we can move it from peg 1 to peg 3. Now here we treat peg 3 as our destination peg. Yeah. Because at the end, all 3 pegs must be moved to peg 3 following the natural order. Okay, yeah. All right, so now the largest disk is on our destination peg. All right, yeah. So here I use, you know, P of 2, yeah, represent the problem of size 2. Yeah, problem size 2, you know, that's the 2-disk problem, right? 2-disk problem, we assume we have the solution. Here, you see that solution. Yeah. So here you can see we need to move the 2 disks on peg 2 to destination peg number 3. That's a size 2 problem, right? So here we need to solve a size 2 problem. Okay, all right. Then how to solve? Yeah, so we move the smallest disk from peg 2 to peg 1. Then the middle disk from peg 2 to peg 3, and the smallest disk this time, the last time, move to the destination peg, peg 3. That's the solution. So you can see after 7 moves, 7 steps, each step just 1 move. So the total after 7 moves, we can solve that 3-disk puzzle. That's our experience. That's our experiment. Okay? Yeah. Because with this experience in our mind, then we feel comfortable to do the further discussion. Yeah. But our next level discussion, we should use the recursion view. Yeah. Here we may not use the recursion view, right? Yeah. Because 3, the number of disks, 3, it's a relatively small size. So we do not need to use the recursion view. So we can handle. Yeah. But when the size becomes a little larger, think about n equals 10. Yeah. N equals 10 without using the recursion view. How can you handle? I cannot. Yeah. I have to use the recursion view. Then I can handle disk 10 case. Yeah. All right. Question. How do we generalize the solution to n disk? Divide and conquer and the recursion. Yeah. So that's what we learned from our computing problem number 6, the factorial problem. Problem size reduction. Here, we will use that problem size reduction. Okay? Yeah. So n disk problem, P of n, that's a n disk problem, right? Then we do size reduction. So we can assume we have the solution of n minus 1 disks. Assumption, all right? Recursion, yeah. Then there is a gap, right? We need to fix the gap. Fix the gap by recursion. Then we can solve it. That's simple. Think about that. Divide and conquer, recursion view, and we solve this relatively hard problem in some simple way. Okay? Yeah. So let's see the details for this part. Yeah. Without using recursion, it is very hard to solve the general case. So, yeah. Because when n equals 10, it's hard. Okay? Yeah. All right. So here you can see, yeah, recursion method, we use problem size reduction. Okay? Yeah. All right. Yeah. So that's the simple idea. Yeah. Still, here we use the size 1 reduction case. Later, we will learn it's not necessary every time you reduce the problem size by 1. Yeah. Sometimes we can reduce more, yeah, more than 1. Okay, yeah. All right. All right, so here, let's look at the general discussion. Yeah. Yeah. Here we still, here, although you see 3 disk, I still use the diagram of 3-disk puzzle, yeah, because it's hard for me to draw n-disk picture. Yeah, hard for me. Okay, so I still use the 3-disk pictures, but we can treat it as, we can imagine there are n disks here. Yeah. All right. So this stack we think, so we treat it as a n disk stack here. Okay. All right. Then, yeah, 3 pegs, we give them 3 different names because later when we write the pseudocode of implementation function, recursive function, we need to use these 3 pegs as the variables, okay, as the parameters. Yeah. So from peg, temp peg, the middle one, temporary, so temp, TMP peg, and the destination, to peg, okay, from to, and the temporary. Yeah. All right, 3 pegs. Yeah. All right. So then we use the problem size reduction way, recursion way. All right, yeah. Here, in order to solve problem of size n here, then we need to solve a problem of size n minus 1. And we can assume we have the solution. Okay, we have the solution. So that means we can move the n minus 1, top n minus 1 disks from first peg to the second peg. Okay, that's the solution. Okay, that's the P of n minus 1 solution. Okay, all right. After that, fill in the gap. We need to fill the gap. Okay, after that, yeah, here, this is P of n. Okay, fill the gap. All right. After, yes, yeah, so, yeah, I need to do, after that, yeah, yeah, here, let me just show you. Yeah. We move the bottom disk to the destination peg, 2 peg, right? 1 move, okay? After that, can we do another P of n minus 1 solution from temporary peg to 2 peg? Just another solution. Yeah. But with 2 different pegs. Yeah. And we know the solution essentially the same, right? Essentially the same as the first time we run the solution. Yeah. The only difference, just the starting peg and the destination peg are different. Yeah. Other than that, the moves you make, yeah, order, yeah, pretty much the same. Yeah. All right. So then we solve the whole problem. We solve that, you know, P of n, the whole problem. Okay. All right. After that, here you can see the general solution when we use the recurrence view. So simple. So simple. Okay. Yeah. Then our implementation is also very simple. Yeah. So based on this view, our implementation is very simple. So my next slide, I show you the pseudocode of implementation. Okay. Yeah. Here, move disks function. Okay. Yeah. So we recursive function. Here we have 4 parameters. The first one, the number of disk, the size number. Okay. Integer size number. Okay. All right. Then 3 pegs. Yeah. From peg, 2 peg, destination, next one. And the middle temporary, we put it as the 4th parameter. Okay. Yeah. So 1, 2, 3, peg one, number 1, 2, 3. All right. Yeah. All right. Then in now the body of the recursive function, yeah, recurrence function, if n greater than 0. Yeah. If n equals 0, so you can print out a message. Right? So there is no disk, you know, things like that. Yeah. Here we just work on the main part. Yeah. When n num, yeah, when num, the problem size is a positive integer, then we do these steps. The first step, recursive function call on size 1 reduction problem, norm -1. But we need to change the peg numbers. From the destination is the temporary one. This, yeah. The destination peg, we make temp peg as the destination and to peg as the temporary one. Okay, yeah. So just a recursive function call. All right. After that, fill in the gap. Yeah. You need to do something after you complete that solution. P of n-1 solution. Okay, after you complete that. So the gap part you need to put, because you move the bottom disk, right? When you move the bottom disk, you need to show people you are doing the work. Okay, you are doing the moving work. So you print out this message. Here I use C++ because that class is C++, right? Here, this one I also borrow from CS3130SP23Module3AVideoAll because that class is C++. Okay, so I use the C++ way. C out, then the message part, move a disk from peg number, yeah, that you print out that the variable, the parameter value. After that, to peg destination, yeah, to peg, yeah, and you finish that message. But after that, you need to move the n-1 disks back to the destination peg. So you need to call the recursive function another one for norm-1 disks. Yeah. But this time you just change the peg numbers, temp from temp, destination to, and the temporary you use from peg as the temporary. All right, yeah. So here you can see for such a non-trivial puzzle problem, we can solve the general case with these lines, very short function implementation. But the problem is non-trivial. Yeah, it could be very complicated, but with this solution, so easy. Yeah, that's the power of recursion. Okay, all right. So let me stop right here. Yeah.